Okay, so let's look at our first problem involving this situation. So we have a particle that's moving along a straight line with the displacement. We're talking about meters and seconds. The displacement function is this. We want to find the velocity of the particle at time t. So we don't have a t to put in, so we're just looking for the derivative of displacement. So let me recopy my displacement function. It's 2t cubed minus 21t squared plus 60t plus 3. And we know that velocity is equal to the derivative of displacement. And like I said before, this is a very good relationship to write down. I'm just going to apply the power rule. So I've got 6t squared minus 42t plus 60. So that's part A. Okay? Part B says find the initial position, the initial velocity. So for the initial position, we're going to use the displacement function, and we're going to substitute in 0. So initial position is where s of 0 is. So that's 2 times 0 cubed minus 21 times 0 squared plus 60 times 0 plus 3, or 3. So 3 meters. So we actually have, I guess you would say, a kind of point going on. At time 0, we're at the 3 meter mark. Okay, we're going to keep that for a problem one of the next letters. For the initial velocity, we're going to substitute in 0 into our velocity function. So that is now 6 times 0 squared minus 42 times 0 plus 60. So our initial velocity is 60. So really what we want to pay attention to with this 60 is we want to see that it's positive, because that's going to tell us that from the initial position of 3 meters, we're going to be moving in the positive direction, or to the right. Okay, so then the next question says, find when the particle is at rest. So for part C, we know rest, implies that the velocity equals 0, and we're looking for when, so we're looking for times. So we have 0 equaling our velocity function, which is 6t squared minus 42t plus 60. I see a quadratic. I'm going to have to factor it, but I see a common factor first of 6, so I'm going to factor that out, and I've got t squared minus 7t plus 10. Oh, that's so much easier. So what multiplies to positive 10 and adds up to negative 7 is I've got negative 5, so t minus 5, and negative 2, so t minus 2. So what that tells me is that it's at rest at time equals 5 and time equals 2. So these are 2 points I'm going to end up putting up here, 5 and 2. That's when this thing will be turning around or changing directions or just at rest. Okay, but I want to find out where that happens. I want to find that displacement. So I'm going to find the displacement at 5. Okay, so I substitute 5 into that equation. So I'm looking at 2 times 5 cubed minus 21 times 5 squared plus 60 times 5 plus 3. I type that all into my calculator, excuse me, and I'm getting a position of negative 168. So that's going to be at negative 168. Okay? And then I want to find the displacement at 2 seconds. So I'm putting in 2, so 2 cubed minus 21 times 2 squared plus 60 times 2 plus 3. I type that all in my calculator and I get 55. So I have another point at 55. Okay. Now, So they didn't get negative. Let me double check that equation I did to get the, oh, that's why, is I substituted in 3 into that first instead of a 5. That's what I did wrong. So the negative 168 is not correct. Let's see what that is. 5. That is actually 28. So let me go ahead and erase that. Real time, making mistakes. Just like in class, that's me. Alright, so that's going to be 28, which means this is going to be 28. So this is going to help us set up our motion diagram in a second. That's why we're writing these down. So that's 28. Oops, and that's 28. Alright, so then we want to find out when the particle is moving left and when the particle is moving right. Well, basically, that's going to happen in between the rest sections. So we start it at 0, and it goes to rest at 2 seconds. So if we actually find out the velocity at 1 second, because that's in between the 0 to 2, that's why we did 1, okay? The velocity at 1 second, I'm going to use my velocity function, so that's 6(1) squared minus 42 times 1 plus 60. What I'm getting is the velocity at 1 is 24. And again, just like down here, what I want to pay attention to is that it's positive. Okay? Now, the other section is between 2 and, I don't like this, this looks like a minus sign, so let's do an arrow, 2 to 5 seconds. So let's pick a number in between those two. 3 looks like a good number there. So I'm doing 3 squared minus 42 times 3 plus 60, and that actually gets me negative 12. And the thing I need to pay attention to there is that it's negative, so it'll be moving to the left. So this is to the right. This is to the left. And then I want to figure out something from 5 on. So let's just do velocity at 6. Okay, so 6 squared minus 42 times 6 plus 60. I type it in my calculator and I get 24 again, which is positive, which means it's going to the right. So the areas where it's going right are when time is between 0 and 2, and when time is greater than 5. Not equal to with any of these, because equal to at these points they're at rest. Left is happening between 2 and 5 seconds. Okay, so the last thing I have to do is draw a motion diagram. So I need a little bit more room for that piece. And basically I'm going to use all of those 3 points that I have on there, and I'm going to use the positives and negatives to give me direction. Okay, so I'm going to draw myself a line. We can go ahead and work in black this time. Okay, so here's my line. My initial position, I always like to put 0 somewhere on this thing. Okay, so 0, all my displacement pieces are positive, so I put 0 down that end as opposed to the middle. And I know I need to have a 3 on there, I need to have a 28 on there, and I need to have a 55 on there. So those are all my displacements, is the 3, the 28, and the 55. So now I need to figure out what happens. Well, here is where my particle starts. That's your initial position. Your initial position is when time equals 0. It's very good to write your time at each one of these spots. So time equals 0. We were at 3 meters. Okay, so what happened after 0 seconds? Well, after 0 seconds, that's 1. It tells us it was moving to the right. So that means we're heading in this direction. Now, where does it first come to a rest? Well, at 2 seconds, it comes to a rest at 55. So we're going to go all the way over to 55. And this is actually where it does a turnaround. Okay, this is my rest point, and that's where time equals 2 seconds. Okay, And then it does a turnaround, and I know it does a turnaround because after 2 seconds, when I went up to 3 seconds, it says it was moving to the left. So we're going to move to the left. Before I start drawing this again, I want to figure out the next time it comes to rest. Well, the next time it comes to rest is at 5 seconds at the 28 mark. So we go over here to the 28 mark, and it comes to rest at time equals 5. Okay? And then what happens after time equals 5? Well, that's when it was moving to the right again. So that means we go like this, and we just draw an arrow at that point. That is a motion diagram. Okay, and I kind of showed you a little bit of that in the part 2 of the last lesson. It was asking for motion diagrams, but that's actually how you would find all those pieces. You want to know directions that's happening. You want to know points of turn. You definitely need to know the initial point. So ultimately, this kind of describes the entire problem situation we've got here. The initial position, it's got a positive velocity, then it comes to rest at 2 seconds at a displacement of 55, and then it starts going a negative velocity. So this could be like something got shot up in the air. Positive velocity came to rest, negative velocity, it's coming back down. Okay, and then, I don't know, maybe it hit a trampoline and it shot back up in the air. Okay? All right.